Now we're going to model the electron as a solid disk which has mass of the electron m sub e, electron mass, and it has a total charge minus e. The charge is residing on the circumference and uniformly distributed, and we're going to assume that this disk is rotating around the z-axis, as you can see in this figure. So basically the model is as follows: a solid disk with uniform mass m sub e, charge residing on the circumference so this is so that you have a charge density lambda is equal to linear charge density, the total charge minus e divided by the circumference 2 pi r. So we have r, the radius of the disk. Okay, so with this model now we have the charge that is going to be rotating dq in a region dl. So if I look at a region dl here, I will see that this dq will be equal to lambda times dl, the arc length. And that is going to be equal to, if I have an angle d theta here, that is going to be equal to lambda dl, which is lambda times r d theta. So I have in this circular arc which has length dl, that is at an angular separation d theta, radial distance r from the center. The total charge that resides on dl is lambda times dl, or lambda times r d theta. Since 2 pi r is the circumference, r d theta is basically the arc length. So dl r d theta is the arc length. Okay, so the current that is going to flow is dq dt. So it's going to be equal to the charge density minus e over 2 pi r times r times d theta dt. So these r's will cancel, and d theta dt is the angular speed, omega angular speed is d theta dt. So I find that the current that flows is going to be given by minus e omega divided by 2 pi. So this is the current that is flowing as the disk rotates around about the z-axis. Then I can calculate the magnetic moment. Then the magnetic moment due to spin I'm going to call this m sub s. M sub s is equal to current times the area of the current loop. So the area of this loop is here, this area A, which is basically the area of the disk. So this will be equal to the current minus E omega over 2 pi multiplied by the area pi r squared. The pi's will cancel, and I will find that the magnetic moment due to spin is given by minus E omega r squared divided by 2. So now my task is to find the connection between this magnetic moment and the angular momentum of the disk. Now, going to the discussion on angular momentum, for angular momentum, basically I have the angular momentum of a rigid object which is rotating about the z-axis. The angular momentum Lz is equal to I omega. Its direction is found by using the right hand rule, so you can curl your fingers along omega. The angular momentum vector is pointing in the z direction, or r cross mv also gives you the same. So for a solid object we have moment of inertia I times omega. So this I is not the current, so this is a moment of inertia. So let me call this Iz because it's moment of inertia about the z-axis, in order to make sure that I don't confuse with the current. And Iz, the moment of inertia of a disk, I can easily calculate. Its integral r prime square dm. So if you consider a mass element on this disk, first of all, in order to find what dm is, I need to know the mass density. Sigma mass density for an areal distribution, which is uniform, is mass of the electron, me, divided by the area of the disk, which is pi r squared. Then I will find that dm is going to be equal to sigma times r prime dr prime d theta. So r d theta, remember, is the arc length. So let me make it clear here. So it's r prime d theta is the arc length multiplied by dr prime gives me the area element. So this is basically sigma times dA. So I can show it here on this disk. So you go to this is your total radius r, and you go to a certain radius, a radial distance r prime, with an angular separation d theta, and here you have r prime d theta is your arc length. So if you also go a distance dr prime here, this is going to be your area element dA. So this is dr prime, this is r prime d theta, so it is r prime dr prime d theta is the area element. Okay, so I can find the differential mass here, dm, to be mass of the electron divided by pi r squared, where r is the total this is the radius of the disk, r prime dr prime d theta, that is dm. Now I have to integrate over all possible dm's to get the total moment of inertia on the about the z-axis. So I can find it is equal to, for dm I have here mass of the electron divided by pi r squared, that will be outside of the integral, and then I will have to integrate over r prime and theta, so I will have r prime cube, so because r prime square is here, so it's going to be r prime cube dr prime, and then the theta, r prime will go from 0 to r, theta will go from 0 to 2 pi, so that I will be spanning the whole area, and this will give me mass of the electron divided by pi r squared. The integral of r prime cube dr prime is r prime to the fourth divided by 4, but between 0 and r this will give me r to the 4 over 4, and the theta integral will give me 2 pi. So I will have a cancellation of pi here, and also the r square will get rid of this one and make it square, and then here I have this 2 giving me a 2 here. So the answer is mass of the electron r squared divided by 2. So that's the moment of inertia about the z-axis. So then I can calculate the angular momentum. The angular momentum will be Iz omega, which is mass of the electron r squared divided by 2 times omega. So I call this the angular momentum p theta due to spin, p theta s. So omega r squared is equal to twice the angular momentum due to spin divided by mass of the electron. So if I go back to my moment of inertia here, so let's go back to moment of inertia. No, the magnetic moment, sorry, not moment of inertia. So we're going back to magnetic moment due to spin. We have found that the magnetic moment due to spin was given by minus e omega r squared divided by 2, minus e omega r squared divided by 2. For omega r squared I can substitute 2 angular momentum divided by mass of the electron. So this will be minus 2, and then I have the electron charge divided by twice mass of the electron multiplied by the angular momentum due to spin. So I substitute for omega r square 2 p theta over p theta s over me, and that's basically the answer I'm getting. So the classical result using this model is for the magnetic moment due to spin is minus 2 electron charge E divided by 2 mass of the electron multiplied by the angular momentum p theta s. So this is our classical result using this model of the electron. Now we find that in quantum mechanics we can write the quantum mechanical result. This is given by ms is equal to minus g electron charge h bar divided by twice mass of the electron times the spin quantum number, let's call this mu s in order to distinguish it from ms, which is the magnetic moment. So this is my spin quantum number. ms. So I find that the quantity in parentheses EH bar over 2me is what I observed also in the classical model for the magnetic moment for orbital motion. So in quantum mechanics we see EH bar over 2me, that's a Bohr magneton. So basically this model gives me well, the quantum mechanical result is minus g Bohr magneton times mu s, which is the spin quantum number. So here I called it mu, not to confuse with ms, which is what I called magnetic moment. So this is going to be the quantum mechanical result, and this g is called Lambda factor, and you can see that the classical result is telling us the Lambda factor is of the order of 2. So it's a pure coincidence that using this classical model we have good agreement between quantum mechanics and classical mechanics. So we will talk about the quantum mechanical model in more detail later on. So let's review what we said about electron spin magnetic moment. We are looking at a model, classical model of an electron, where we think of the electron as a solid disk with uniform mass distribution but non-uniform charge distribution, in the sense that charge is uniformly distributed around the circumference, not through the area. We have a linear charge density minus E over 2 pi r. The differential charge that is rotating with the disk is lambda dl, lambda times the arc length dl, which is r d theta. And so we find that the current dq dt is minus E over 2 pi r, which is lambda times r d theta dt, because r is not changing, and r's cancel. The angular speed is d theta dt, which is omega. So the current is minus E omega over 2 pi, and the magnetic moment is current times the area, which is minus E omega over 2 pi times pi r squared. That gives us minus E omega r squared over 2. Now, what is the direction of this magnetic moment? Well, you can see that the electron has a negative charge, so if you follow the direction of the current, if the electron is basically spinning in the direction of omega, then you have to consider the opposite direction in order to get the magnetic moment. So it's going to be pointing down in the minus z direction using the right hand rule. Now, the angular momentum for a solid disk is Iz omega for rotations about the z-axis. So this is going to be found by calculating integral r prime squared dm. The mass density is mass of the electron divided by pi r squared. Remember, I'm assuming uniform mass distribution. So for a differential mass element, I can calculate sigma dA, which is sigma r prime d theta dr prime. And if I integrate it over all possible radial distances from 0 to r and all possible angles from 0 to 2 pi, I obtain mr squared over 2 as the moment of inertia. So the angular momentum is mr squared over 2 omega. So omega r squared is twice the angular momentum divided by mass of the electron. If I substitute this result for omega r squared in the spin magnetic moment, ms, I obtain minus 2e over 2me p theta s. P theta s is the angular momentum due to spin. And so this result in quantum mechanics, the corresponding result is minus lambda factor eh bar over 2me m sub s, which is the spin quantum number. Here I made it mu in order to distinguish from the spin magnetic moment. So you can think of h bar times m sub s or mu sub s as the angular momentum. So you have angular momentum times e over 2me times lambda factor g, which is of the order of 2 according to the classical calculation that I have made here. And this is the quantity in parentheses eh bar over 2me is once again my Bohr magneton. So I have the lambda factor Bohr magneton times the spin quantum number m sub s, giving me the magnetic moment with a minus sign, of course, is giving me the magnetic moment due to the spinning electron.